Hi, let's take a look at applying a relativistic Lorentz coordinate transformation. So, say that we have a clock that's traveling at the relativistic speed of 0.6 times the speed of light. And it's traveling along an observer's x-axis, and the moment that clock passes the origin on the x-axis, its time reads exactly 0 seconds. What would that clock read after it passes the 180 meter mark in our stationary observer's coordinate system? Well, anytime we're dealing with relativity, one of the first things we're always going to need to do is calculate our Lorentz factor gamma. 1 over 1 minus v squared over c squared, all under a square root. So, 6 tenths is 3/5. I square that, I'd give me 9/25. So I would get 1 over 16/25, which would be 25/16. So that means for 0.6 times the speed of light, our Lorentz factor is 1.25, 5/4. Now, if we want to compare the moving observer's coordinates to the stationary observer's coordinates, which is what we would need to do to find the time displayed by the clock, well, time and space are linked in relativity. So the moving observer's x-coordinate, their change in position they observe, would be equal to the Lorentz factor gamma times the quantity of the stationary observer's change in x minus the relative speed times the stationary observer's change in time. And the time observed by the moving observer, which would be the time on the clock as it flies past, would be equal to the Lorentz factor gamma times the quantity of the time measured by the stationary observer minus the relative speed divided by the speed of light squared times the change in position measured by that stationary observer. Well, we want to calculate delta t prime. We have a measurement for delta x. We said it's traveling 180 meters, but we don't have a measurement for delta t directly. However, we do know the speed of this object. And that object is traveling at a constant speed of 0.6 times the speed of light, and it travels at that speed for a distance of 180 meters, which means our time would be equal to our distance divided by our speed. Basic Chapter 2, Welcome to Kinematics equation. Well, one of the neat things with Lorentz transformations can end up giving you the time dilation equation and the length contraction equations that we worked with earlier in this chapter. So, if I plug in for delta t, delta x over v, then I'll have gamma times the quantity delta x over v minus v over c squared times delta x. I can factor out a delta x, and I can also factor out a 1 over v. And to make it possible to factor out a 1 over v, I would have to multiply and divide the second term by v, so the v in the denominator goes outside. And just as a reminder of what gamma is, it's 1 minus v over c quantity squared raised to the minus 1/2 power. Factoring out that delta x over v, I get 1 minus v squared over c squared, which is the same thing, but to the 2/2 power. So 2/2 minus 1/2 means that I get 1 minus v squared over c squared to the 1/2 power, and this piece right here is just 1 over our Lorentz factor gamma. So that means that the time measured by our clock, which in this case would be our proper time, would be equal to delta x over v, which is the time measured by the stationary observer, the improper time, divided by gamma. That's time dilation. But in terms of the distance we know and the speed we know in gamma, 180 meters divided by 5/4 divided by 3 times 10 to the 8 meters per second gives me 0.80 microseconds. And the dilated time would be the proper time of 0.8 microseconds times 5/4, which would be 1.0 microseconds. And if we were to apply the same logic looking at delta x, and we were to factor our delta t out of the equation over here in the same way, we would end up getting exactly the same equation that we would get with the length contraction equation. Thanks for watching.